Hi folks, Frank here. In this little tutorial I'm going to show you how to do the crater counting in Word, how to take your actual crater numbers, convert them to normalized crater numbers, and how to plot those normalized crater numbers on the graph for isochrons. So let's get started. This is the Word document. Second page is, second and third pages are the images with the craters. This large feature is not a crater, so you don't have to worry about it. And you also don't have to worry about all the little red dots, which are the craters in the 0 to 8 kilometer range, which we have already marked. So you really only need to count the craters that are bigger than the red dots. Now to do that, it helps to zoom in quite a bit. Let's go to 200%. Scroll to the bottom of the first page. Okay, and you can see the little red dots in some cases are sitting above craters that you can actually identify. You see that we have four colored circles. The yellow circle is for the 8 to 16 kilometer range. The green circle is 16 to 32. The red is 32 to 64, and the blue is 64 to 128 kilometers. Any crater greater than the blue circle you do not need to measure. So to measure it, so we have, let's look at some craters. Here's a crater that's reasonably sized. Here's a smaller crater. There's another large crater over here. We'll grab the smallest circle. You can see little handles appear on it. If you stay in the where the yellow colored line is, you'll have a cursor that is a little crosshair, and you can drag it. This and this crater, these craters are clearly too large for that. On the other hand, this one is perfect for it, so you place that over top of it. You have just counted one crater in the 8 to 16 kilometer range. Now you want to leave this point there, and you want to have another circle that you can use. So if you've moved away, it's no longer highlighted. Just simply click on it again. On the keyboard, press Ctrl D, it duplicates it, and then you can move it, and okay, this guy also looks like it would fit. For this crater, let's see if the green one fits. Yeah, looks like the green one fits, so that is in the 16 to 32 kilometer range. Oops, I was going to duplicate it, so let's duplicate it. On the other hand, if I put it into this crater, it's too small, which means for this I would need the red circle. So what you need to do, don't leave any of these things lying about. What you need to do is click your way through the image, placing all the various circles and then counting them. If we then go, let's say you had counted, we'll look at this plot, this table here. If you, for example, had 100 craters in the 8 to 16 kilometer size range, you enter 100 in this cell. The plot to actually get the ages is calibrated to an area of 1 million square kilometers. The image that you've measured is greater than 1 million square kilometer. The image that we gave you is 1.4 million square kilometers. So you need to normalize this value to number of craters per 1 million square kilometers. How do you do it? Simple. You grab a calculator and you enter the number of the actual craters, 100, and your image is bigger than the normalized image, which means that you divide your number of craters by 1.401 for 1.4 million square kilometers. and you get a value of 71.4 if we round off to the nearest decimal place. So you enter 71.4 into this cell, and this is the number that you're going to plot on the graph, which is right below. Now, before we plot anything, let's have a quick look at what's on this graph. On this side is the scale of craters per 1 million kilometers, and it's a logarithmic scale, so it goes from 0.1, 1, 10, 100, 1000. The little subdivision in between, if we start at 1, this would be 2, 3, 4, 5, 6, 7, 8, 9, 10. On the next one, if we start at 10, this would be 20, 30, 40, 50, 60, 70, 80, 90, 100. So you can see that the difference between 71.37 and 71.4 is not something you're going to plot on this, because the subdivisions up here are really quite small. Along the bottom axis, we have the crater diameter in kilometers. Now, the 71.4 value that you had was for the 8 to 16 kilometer size range. So you're going to put one plot in the middle of that range, which is 12. So you grab one of these convenient dots. We give you 4 dots for one image in blue, 4 for the other image in red, and 2 lines, and I'll show you how to do the line in a second. You grab one of these points. Let's say I'm going to plot this along the 12th axis, and my value was 71.4, so I need to place it up here. There it is. The next range was 16 to 32, so the halfway mark is 24, so I'm just going to grab it and arbitrarily plunk it down there while you have actual numbers. The next one was 32 to 64, midpoint is 48, so it's going to go, let's say we'll have a value there. And the last size range was 64 to 128, so I'm going to grab this and I'm going to, oops, I didn't grab it, no I did grab it, grab it again. I'm going to put this in the halfway, which is in the 96 kilometer, on the 96 kilometer axis. So we have 4 points, which ideally should be in a line, and ideally these points should be parallel to these lines. In reality, that's unlikely to be the case. So you have to find a best fit line, and this is why we give you these these preset lines. These lines on the graph are isochrons, and the best fit line that you have to fit needs to be parallel to these lines. So you can, let's say I believe my best fit line is approximately there, and I'm going to extend it. I want to extend this line beyond the axis, because that's where I'm going to read stuff off in a second. I'm just going to zoom in a little bit more to text width, just to make it a little clearer. So be careful not to change the slope of the line this way or this way. Keep it parallel to the actual line. Okay, so we've placed our best fit line. Now comes the time to read the H. Where these isochrons, these sloped lines, intersect this axis, that is what gives you the H. So this is a 4.4 billion year isochron. This one is 4, 3.7, 3.5, 3.2. This lowest value down here is 0.7 or 700 million years. Where my blue best fit line intersects is just above 4, but well below 4.4, so I'm going to have to estimate what the value would be. I would say this would be about 4.2, so maybe I'm at about 4.1 billion years. So the value that I'm picking for my 4 points, all of which were chosen arbitrarily, is about 4.1 billion years. You'll do the same thing for the other image using the red lines, and you'll have another value for that. And these two values, where I've placed the line right now is at about 3.7. So let's say, for example, your values are 4.1, 3.7. Those are the ages that you record on the next page and use to answer the remaining question. And hopefully that clears up any uncertainties you may have about this assignment.